All right, morning today. We're moving on in bonding. We're going on to covalent compounds, which anything that's covalently bonded is called a molecule. So that's why we call this molecules. And then we're going to do the naming of covalent compounds, which is similar, but with a little bit added step compared to ionic compounds. Okay, first things up is your bell ringer. Okay, so looking here. So when you are doing figuring out the oxidation number for iron or oxygen in this case, you do need to have your periodic table available to you. And we do a process called reverse crisscrossing. So here, the 3, that's a subscript of O here, came from the iron. So iron is probably a +3. If you look on your periodic table, iron can be a +3. And this 2 came from the oxygen, which is up here as a -2. All right, so the oxidation number for iron in this compound here would be +3. Now remember, the name of this compound is iron, Roman numeral 3, oxide. All right, iron needs to have a Roman numeral in its name because it's a transition metal. So just trying to refresh you on all those rules. Now the second one, all right, if you look at iron can be a +2 or a +3. Sulfur can be a -2, a +4, or a +6. So the only way that it can end up with a 1-to-1 ratio is if sulfur is a -2, and then therefore iron's got to be a +2. So the oxidation number of iron in this compound would be iron, Roman numeral 2, or +2, I'm sorry. The name of the compound is iron, Roman numeral 2, sulfide. Okay? All right, so the oxidation number in the first one is +3. The oxidation number in the second compound is +2. Just depends on what the formula of the compound is. Okay, so today we're going to continue on with our bond type. We talked about ionic compounds last class, which were bond between a metal and a non-metal atom. The electronegativity difference was great, which means it's 2.0 or higher for the Regents level. For that's their designation. Which means what happens is one atom will gain an electron, one atom will lose an electron, and it will form an ion, a positive ion, a negative ion. And then the bond is created because those two oppositely charged particles are attracted to each other. Okay, so continuing on, we do have to look at electronegativity differences. So today we're going to talk about covalently bonded things. All right, in covalently bonded compounds, they don't transfer electrons, or one thing doesn't gain and one thing loses electrons. They actually share electrons. All right, it's a bond between two nonmetals, so the atoms on the right-hand side of the periodic table. All right, the electronegativity difference for a covalently bonded substance is less than 2. Okay, so here you're going to have not a great separation of charge. All right, so what happens is there's not the ability for one electron to be pulled away from another, or one atom to lose an electron, shall we say, depending on which perspective you want. All right, so what they ultimately end up doing is they end up sharing an electron, or 2 electrons, or 3 electrons. All right, so go back to the dog analogy. All right, here we have 2 dogs, 2 large dogs, because they have to be non-metals. Remember, the large dogs were the non-metals and the little dogs were the metals. All right, 2 large dogs, and they both want this Frisbee or this toy, whatever that is. All right, and what happens is one might get it for a little bit, but then the other one's going to get it back, and they're going to kind of play tug of war for, as long as they both want that toy. All right, and that's kind of what happens with electrons. It's kind of in that tug of war between the 2 atoms. All right, and because neither atom is significantly stronger than the other, i.e. more electronegative, all right, then what happens is they end up both saying that electron is mine. It's kind of like you guys walking down the hallway or in the lunchroom, if there was such a thing this year, all right, and you see a $50 bill on the ground. You and somebody else both pick it up at the same time. You both want to claim it as yours, all right, and you got to figure out some way to divvy it up or whatever. Okay, all right. So as a result, because there's not a strength to pull one electron away from the other, it can't form an ion. It can't form a charged particle. All right, so here we go. So let's figure out if the compound between carbon and chlorine would be ionic or covalent. To do that, you have to look up electronegativities on table S. Remember, table S is on your reference tables. So you look up carbon's electronegativity, you should be pausing and doing this. Carbon's electronegativity on table S is 2.6. Chlorine's electronegativity on table S is 3.2. When you do the difference between those, it doesn't matter if it's negative or positive. All right, the difference between those two particles is 0.6, which is definitely less than 2. So that means that in this case, even though chlorine's more electronegative than carbon, all right, it's not significantly more so electronegative, so it doesn't pull the electron to it, or carbon doesn't lose the electron to chlorine. All right. Ooh, one of our diatomics, iodine. So what's the electronegativity difference in this one? All right. Whatever iodine's electronegativity value is, if you look it up on table S, all right, it's 2.7. So in this case, it's 2.7 minus 2.7, which is 0, which is definitely less than 0 or less than 2. All right. So therefore, this is going to have, these are actually two different types of covalent bonds. This is said to be what's called a polar covalent bond, and this is a non-polar covalent bond, which we'll talk about in the next slide. Okay, so this one's a complete equal sharing of electrons. Okay, so I kind of let the cat out of the bag there a little bit. All right, we're going to talk about there's two types of covalent bonds. All right, generally they both are bonds between two nonmetals, but depending on how they share the electrons will determine what type of bond it is. All right, there's what's called a polar covalent bond. All right, and I don't use this terminology. We're going to talk in the next couple of classes about polar covalent bonds and polar covalent molecules, which are not the same thing. So you have to get this straight in your head. Okay, so a polar covalent bond, simply put, is something that has an electronegativity difference of 0.5 up to 1.9. All right, and it results in the unequal sharing of electrons. So what I just said there is the electronegativity difference is from 0.5 to 1.9. So this is on the bigger side of difference in covalent compounds. All right, if you get to college and they do the 1.7 cutoff, then it's 0.5 to 1.7. All right, those compounds between 1.6 and 2.0 are, oh, we hit the bell tones. All right, are in that range of, they can be kind of ionic character and covalent character. All right, but what a polar covalent bond is an unequal sharing of electrons. One atom is a little bit stronger than the other one, so it gets it a little bit more. It's kind of like a 4-year-old and a 2-year-old fighting over a toy. The 4-year-old is probably a little bit smarter and can distract the 2-year-old and get the toy a little bit more. All right, so if we look at this compound right here, now when you're doing the electronegativity differences, the subscripts don't come into play at all. All right, they have no factor in there whatsoever. All right, so here you have iron with an electronegativity value on table S of 1.8. Oxygen has an electronegativity value of 3.4. So if you do the difference between those two, hopefully you can do it without a calculator, but if you can't, use a calculator. All right, you get a difference of 1.6, which is definitely in this range of 0.5 and 1.9. So that makes this compound here a polar covalent compound. Now, even though it's a metal and a nonmetal, all right, which remember, metals and nonmetals normally would be ionically bonded, but if we have to do the electronegativity difference to ultimately determine what type of bond it is, okay? All right, so what happens is it results in partial charges. So in this case, because the oxygen is more electronegative than the iron, oxygen is going to be a partially negative side to the molecule, and iron is going to be a partially positive side to the molecule. All right, so whichever one's more electronegative is going to be more negative, whichever one's less electronegative is going to be more positive. Non-polar covalent bonds results from the sharing or the equal sharing of electrons. All right, electronegativity difference is really small on these, so 0 to 0.4. All right, realistically speaking, most of the non-polar covalent bonds are diatomics. There are a handful of other ones, but for us, it's pretty much the diatomics. All right, so it's usually only in the diatomics. Hopefully you remember the diatomics: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. All right, Han 17, Brinkelhoff, have no fear of ice cold beer. All right, you do have to remember those. All right, so if you do oxygen, oxygen's electronegativity, you look up here, we already have it as 3.4. So 3.4 minus 3.4 is 0. All right, so in a diatomic, they're completely sharing the electrons equally. So, oxygen is actually going to have a double bond in there when we get to this point. All right, oxygen would be sharing 2 pairs of electrons or 4 electrons total. All right, and neither atom is going to give them up. So both atoms of oxygen are going to claim them as theirs. Okay, so that's kind of what bond type. How do you figure it out? Now we're going to talk about naming covalent compounds. All right, generally speaking, the rules are similar. We just need to add one thing. We have to add prefixes. And the prefixes are used to represent the number of atoms there are in that particular molecule. All right, and we have to know the prefixes for numbers 1 through 10. These are very specific for covalent compounds. Some of them you will recognize, some of them you might not recognize. All right, but remember, prefixes are words that you stick in front of other words to represent the number of them. All right, in this case, the number of them. So like a tricycle is a cycle with 3 wheels. So tri is a prefix. All right, so if we look here, prefix for 1 in covalent compounds, all right, and we'll have different prefixes when we get to organic. All right, but prefix for 1 in covalent compounds is mono. All right, like, you guys have heard of mononucleosis. All right, prefix for 2, all right, is di. Not bi. Bi is every other, but di. Like you guys, hope if you took living environment, you learned about a disaccharide. All right, and we could go back here to mono. In living environment, you learned about monosaccharides. So 1 is mono, 2 is di, 3 is tri. Like I said, with a tricycle, all right, or tricycle. All right, prefix for 4 is tetra. All right, because those people that play Tetris, if you've ever heard the game Tetris, if you think about the game pieces in Tetris, they all are made of 4 boxes. All right, so it's kind of cool. People don't realize it. Now it's kind of one of those trivia things. All right, so 4 is tetra. All right, like a tetrahedral shape. All right, 5 is penta. All right, like a 5-sided figure. I think you guys are familiar with that. Prefix for 6 is hexa. Prefix for 7 is hepta. 8, everybody seems to know 8. 8 is octa. 9 is nana, nana, nana. All right, and then 10 is deca. All right, so these prefixes you have to memorize. All right, you have to know them. You have to know them quickly. And we use them to name compounds. Now, I'm going to just go over a handful of problems today with covalent naming. All right, and then realistically, how you get this down is you practice. That's what the homework is for. All right, and then after next class, I can give you worksheets with both ionic and covalent on there, and you have to be able to name them both. And remember, ionic compounds don't have prefixes. We don't use these prefixes on ionic compounds, but covalent compounds do. And how do you determine if you name it ionically or covalently? Is you do electronegativity difference. Okay, now one thing I do want to point out is if it has a polyatomic ion in it, like a table E1, you don't use prefixes. That's going to be named ionically. All right, but we'll talk about that. Okay, so here we go. We got these 2 compounds. We got CO2 and we got CCl4. Okay, so chemistry always has extra rules. So how many carbons are there here? All right, we don't write it, but it really has a 1. So it's 1 carbon and 2 oxygens. When the first element in the compound is 1, we do not use the prefix mono. All right, so like if you were to name this up until now, what I'd said, this would normally be carbon oxide, but then we got to put prefixes for the numbers. So it'd be monocarbon dioxide. All right, but because the first one is a 1, we don't use the prefix mono. So this one is just called carbon dioxide. So carbon dioxide, 1 carbon, 2 oxygens. Okay, so we come down to the second one. The first element is carbon. All right, but there's 1 of them, so we don't call it monocarbon. We just go carbon. And then we need the prefix for 4. Prefix for 4 is tetra. And then chlorine becomes chloride. So this is carbon tetrachloride. All right, so that's taking the formula and getting the name. All right, now we'll take the name and get the formula. So you've got nitrogen and oxide. So nitrogen is N, capital N. Oxide means oxygen, which is capital O, so it'd be NO. All right, but you have dinitrogen. So dinitrogen means N2. And oxygen means O. Monoxide means one oxygen. So it's N2O. All right. And then we have diphosphorus pentoxide. So you got phosphorus, which hopefully you know is P. You got oxide, which means oxygen, which is O. So you have diphosphorus, so it's P2. And then pentoxide, which is O subscript 5. P2O5. All right. And then our last one is H2O, which you guys I'm sure are familiar with as being water. That is not its technical name. All right. It is a covalent compound, so you should name it covalently. So you have hydrogen and you have oxide. So it's something with hydrogen oxide. There's two hydrogens. So it's dihydrogen, and then it's monoxide. Dihydrogen monoxide. Okay? All right, so that wraps up naming covalent compounds. Tonight you're going to get some practice with that, and then make sure you know how to name ionic compounds as well, because we're going to kind of roll between the two. All right, but we are done for today. Have a great day.